Welcome to AI Paper Podcasts. Today, we're diving into something pretty exciting. Making AI generate realistic videos that last, longer than just a few seconds. We're talking minutes, maybe even telling a whole story.
Yeah, it's a huge challenge. The big problem has always been, AI video amnesia. How do you get a model to remember what happened at the start of the video by the time it gets to the end?
Right, without the characters changing faces or the scene just falling apart. And traditional methods like diffusion transformers, they just hit a massive wall, computationally speaking.
It's that quadratic cost, O of L squared. If L is your video length in tokens, the compute needed just explodes. For like a 1-minute video at 480p, that's maybe 180,000 tokens. It's just possible with standard self-attention. The model basically forgets.
Okay, but this is where our paper comes in. A team led by Sheng Kuai from Stanford and ByteDance Seed, they've come up with something called mixture of contexts, or MOCI.
And it's a really clever shift in thinking. They frame it not as brute force, but as an internal information retrieval task. Like the AI learns to search its own memory.
So instead of trying to process everything, it just picks the important bits.
Exactly. It dynamically selects only the most relevant chunks of context for whatever it's generating at that moment. Think of it like a really smart adaptive memory.
And the results, you mentioned efficiency.
Oh yeah, big time.
Yeah.
Near linear scaling. They cut down the attention computations, the FLOPs, by up to 7 times.
7 times.
Yeah. And that means speeding up minute scale video generation by 2.2 times. So you're getting these longer, minute-long videos for roughly the cost of short ones.
And crucially, it helps with that consistency problem, the AI remembering things.
Massively improves coherence. Identities, actions, scenes, they hold together much better over time.
This is actually the first work showing that this kind of learned, sparse context routing can beat those practical barriers of quadratic attention. It unlocks real long-term memory for video gen.
Okay, this sounds like a major leap. Let's unpack how they actually pulled this off. So this video amnesia you mentioned, it's not just about the compute cost. No, not entirely, though the compute is a huge part of it. That OL2 scaling is brutal. Again, 180,000 tokens for a minute of video. The memory and processing power needed for full attention is just wild. Intractable, really.
Right.
But even if you had infinite compute, there's still the challenge of teaching the model what context matters. How does it selectively recall the right past information at the right time, without the main character suddenly looking different or the background shifting randomly? That's the core learning problem.
So previous attempts tried to fix this, maybe by compressing the past video into keyframes or something, or using fixed patterns to ignore certain parts.
Yeah, people have tried those things. Compressing history into keyframes or latent states, or using fixed sparse patterns where you say only attend to every 4th frame.
But what's the catch there? What do you lose?
Well, that's the key question, isn't it? How much detail gets lost? If you compress history, you inevitably throw away information the model might need later. Think subtle facial expressions or background details.
Oh.
And static sparsity, where the pattern of what you ignore is fixed, that just can't adapt. Maybe for this frame, the context from 30 seconds ago is crucial, but a fixed pattern might just skip over it. So it limits preserving those really long-range dependencies that make a story coherent.
So this paper tackles that limitation head-on.
Exactly. It's about teaching the model to remember smarter, not just harder, or by throwing information away.
Right. And this reframing you mentioned, from brute force attention to internal information retrieval, that sounds like a really fundamental shift. What does that actually mean for the model?
It means the model isn't just passively looking at all the past data points. It's actively searching through its own internal representation of the past video, trying to find the specific pieces of information that are most relevant to generating the current frame or token.
Like how we recall a specific memory when needed, rather than replaying our entire life history?
Precisely. Mosaic sets up this adaptive framework. Each little piece of the video being generated, each query token, dynamically figures out which past chunks of context are most useful. And it does this using a learnable, sparse attention routing mechanism. It's not static. It adapts on the fly.
Okay, mixture of contexts. So how does this dynamic selection actually work under the hood? How does it pick those relevant chunks?
So first, they partition the whole video stream, which includes the visual frames and any text captions, into what they call content-aligned chunks, along frames, shots, caption boundaries.
Content aligned, not just fixed size blocks.
Right, that's important. Then, for every query token, There's this router, it's actually parameter-free but trainable, which is clever, that uses a top-next selection. It looks at all the available past chunks and picks, say the top 4 or 8 most relevant ones.
Top next selection. Okay. But you also mentioned mandatory anchors. That sounds important, like a safety net.
It absolutely is. These are crucial for stability and making sure vital information isn't accidentally ignored by the dynamic router. There are 2 main types.
What are they?
First, cross-modal links. Every visual token always gets to look at all the text tokens from the prompt. Text carries so much semantic weight. The overall style, who the characters are, key actions. This stops the model drifting away from the prompt.
Prevents prompt drift. Got it. And the second type?
Intra-shot local window links. This basically forces tokens within the same camera shot to attend to each other, or at least to their immediate neighbors within that shot. It helps maintain continuity of motion, lighting, object appearance within a single scene.
So it handles the short-term consistency within a shot.
Exactly. Which frees up the sparse dynamic attention budget, that top PX selection, to focus on finding the really important long-range connections across different shots or moments in time. Without these fixed anchors, the model might waste its limited attention budget just trying to maintain basic local coherence.
And there was one more piece, a causal routing mask.
Yes, very important. This prevents weird feedback loops. Imagine chunk 5 thinks chunk 6 is relevant, and chunk 6 simultaneously thinks chunk 5 is relevant. They could get stuck just attending to each other, ignoring the broader context.
Like an echo chamber.
Kind of, yeah.
Mm-hmm.
It can lead to stalled motion or repetitive loops in the video. The causal mask forces chunks to only attend to earlier chunks in time. It ensures information flows forward, creating a directed acyclic graph, which leads to more stable training and better long-range dependencies.
Wow. Okay, so you've got this dynamic selection finding relevant long-range stuff, fixed anchors handling prompt and local consistency, and causality preventing loops. It sounds quite elegant, actually.
It is, and the efficiency gains come almost as a byproduct of this intelligent structure.
Right. You mentioned the numbers earlier, pruning 85% of token pairs, 7x fewer FLOPs.
Exactly. Which leads to that 2.2x speed up for generating minute-long scenes, around 180K tokens. It makes training and generating these long videos actually practical.
Okay, let's dig a bit deeper into the mechanism. Vanilla attention calculates interactions between all query key pairs. How exactly does Mochi modify that equation?
So standard attention involves that softmax over all possible key scores for a given query. Mochi introduces this routing layer before the main attention calculation. The top-grade router selects a subset of key chunks. Then the attention calculation, that softmax, is only performed over the keys within those selected chunks, plus the mandatory anchor chunks.
And the relevant scoring for that top guy selection, how's that done without adding a ton of parameters?
This is one of the really neat parts. They use mean pooling. For each chunk of context, they just average the key vectors within that chunk to get a single descriptor vector.
Just averaging. That seems surprisingly simple.
It does, but it works remarkably well for video. Video data has a lot of redundancy, right? Consecutive frames are often very similar. Mean pooling effectively captures the dominant semantic features of that chunk pretty robustly. It cuts through the noise.
Okay, but if the top K selection itself is non-differentiable, you just pick the top K, that's a hard decision. How does the model learn which chunks are actually relevant? How do the gradients flow?
That's the clever bit. The learning is indirect. The gradients from the main diffusion loss flow back through the attention mechanism, but only through the connections to the chunks that were actually selected by the router.
I see.
So if the router picks a chunk that turns out to be irrelevant for the task, the gradients flowing back will effectively teach the query and key projection layers to produce representations that make that irrelevant chunk less similar to the query next time. Over time, the network learns to shape its query and key representations so that the simple dot product similarity used for routing becomes highly effective at picking the genuinely useful context.
So the network learns to make the simple routing mechanism work better without the router itself needing complex, learnable parameters.
Exactly. It keeps the routing lightweight, but still highly expressive and trainable.
They also mentioned some regularization techniques. Context drop-off and drop-in. What's that about? Sounds like intentionally messing with the context.
It is, yeah, but in a good way.
Yeah.
It's similar to tackling issues like dead experts and mixture of experts models. You want to make sure the model isn't overly reliant on just a few context routes and that all parts of the system stay active and useful.
Okay.
So context drop-off means during training, they randomly remove some of the chunks that the top cake router selected. This forces the model to cope with incomplete context, making it more robust and encouraging it to find redundant pathways or rely more on the anchors if needed.
Makes it less fragile. And drop-in.
Context drop-in does the opposite. It randomly adds a few extra, potentially irrelevant chunks into the mix that the router didn't select. This forces gradients to flow through a wider variety of chunks, even less frequently selected ones, preventing them from becoming completely ignored or dead. Both techniques together help balance context utilization and make the whole Marcy framework more robust.
Makes sense. It forces the model to be flexible. Now, you mentioned content-aligned chunking earlier. Why is that so much more important for video compared to, say, just chopping up text into fixed blocks?
Because video is much more complex structurally. It's not just a 1D sequence like text. You've got the 2D spatial layout of pixels within a frame, the temporal dimension across frames, potentially multiple camera shots with cuts, and you have the text modality from the prompt.
Right, it's multidimensional.
Exactly. If you just used uniform-sized chunks, you'd inevitably cut across frame boundaries, shot boundaries, or mix text tokens with visual tokens within the same chunk. This would muddy the waters for that mean pooling descriptor. The average wouldn't represent anything semantically coherent.
Ah, okay.
So by partitioning along content-aware boundaries, making chunks correspond to single frames or whole shots, or just the text tokens, they ensure each chunk is relatively homogeneous. This keeps the mean pooled keys more discriminative and makes the retrieval process much more meaningful and effective.
That clarity in the chunks is key for the retrieval to work well. And we talked about the fixed anchors too, always attending to text and always attending within the current shot.
Yep, those are non-negotiable connections. The cross-modal one ensures the model stays true to the prompt, maintaining global style, character identity, things like that. Text is information dense.
And the inter-shot one?
That handles the local smoothness, object trajectories, lighting staying consistent within a scene. By making these connections mandatory, you guarantee that local coherence, freeing up the sparse attention to focus its budget on finding those crucial long-range dependencies between different shots or distant moments in time. It also helps prevent jarring visual breaks when a scene cut happens.
And that causal mask preventing loops. It sounds like without it, the sparse routing could actually hurt long-range coherence in some cases.
It could, yeah. Sparse attention introduces directionality. But without control, you could get these pathological closed loops. Like chunk A attends to B, and B attends back to A, forming an isolated cycle. Information gets trapped, gradients might not flow properly across the whole sequence.
Leading to stalled video or repetition?
Exactly. The causal mask explicitly prevents chunks from attending backwards in time during routing. It forces the interaction graph to be a directed acyclic graph, DAG, ensuring information flows progressively forward. This promotes richer long-range dependencies and just makes the whole training process much more stable, especially for these really long, minute-scale sequences.
Okay, all these pieces, dynamic routing, smart chunking, fixed anchors, causality, they paint a picture of a really well-thought-out system. But the proof is in the pudding. How does it actually perform? You mentioned the efficiency gains, but how is that achieved in practice?
Yeah, the engineering side's pretty impressive too. They didn't just get theoretical FLOP savings, they made it work fast in practice. They used highly optimized implementations, particularly flash attention kernels, which are designed for efficient attention computation, especially with sparsity.
Flash attention helps a lot with memory and speed, right?
Definitely. They did clever things like calculating the mean pooled chunk descriptors on the fly, using segment-reduce operations, avoiding the need to actually create and store separate chunk data structures. They organized the tokens carefully for efficient memory access and managed to wrap the whole routing and attention calculation into a single efficient kernel call. It's optimized specifically for the structure of video data.
So the numbers again. 7x FLOP reduction.
Yep, for a minute-long 480p video, roughly 180K tokens, the attention cost drops from about 1.66 E13 FLOPs with dense attention down to about 2.32 E12 FLOPs with moles. That's over a 7x reduction. And crucially, the cost now scales almost linearly with sequence length, L, not quadratically, L2.
And the measured speed up.
About 2.2 times faster end-to-end generation for those minute scale scenes, compared to a dense attention baseline if it were feasible. That's a real practical speed up.
Okay, speed is great, but the quality, did they have to sacrifice visual fidelity or coherence to get that speed?
That's the amazing part. No, quite the opposite.
Wow.
For shorter, single-shot videos, even with 83% sparsity, Mochi actually matched or beat the dense baseline models on standard video quality benchmarks like VBench.
VBench checks things like consistency, motion.
Exactly. Subject consistency, background consistency, motion smoothness, how dynamic the motion is, aesthetic quality, basic image quality. Mochi performed really well across the board.
And for the really long videos, the minute-long ones.
That's where it shines even more. With 85% sparsity on 180K token sequences, May significantly boosted performance, especially in motion diversity. The dynamic degree metric went up substantially, meaning less static or frozen video, while maintaining high scores on all the other quality metrics. The paper has some great qualitative examples like a TV rotating smoothly for a full minute, or a mammoth walking where Mochi maintains consistency far better than the baseline models.
That's impressive. And you mentioned earlier they even tried a zero shot, just plugging Mochi into an existing pre-trained model.
Yeah, that was a cool experiment. They took a model trained with dense attention and just swapped in the Mochi attention layers without any fine-tuning, just setting a sparsity level, like 75%. And it still worked reasonably well, maintaining decent consistency.
What does that tell us?
It strongly suggests that the core idea, using mean pooled descriptors for relevance in routing context, is fundamentally sound and doesn't necessarily require extensive training just for the routing part to work. The pre-trained query key projections already contain enough semantic information for the routing to be somewhat effective. Fine-tuning just optimizes it further. It speaks volumes about the robustness of the design.
And it wasn't just tied to one specific model architecture. They tried it on others.
Right, the appendix shows it working well on different model backbones too, like WAN 2.1. It suggests Mochi is a general technique, not just a trick tailored to one specific setup. That's really promising for its wider adoption.
So, looking forward, what are the limitations right now, and where does this research go next?
Well, the authors are pretty upfront about it. While they've achieved great results and significant speedups, the current implementation still relies on somewhat general-purpose, variable-length attention kernels. Given that they're saving over 7x in FLOPs, there's potentially even more speed to be gained through more specialized hardware-software co-design. Think custom CUDA or Triton kernels built specifically for this Mochi routing plus attention pattern, maybe fusing the operations more tightly. That could unlock further efficiency gains, making it even faster.
And in terms of applications?
Exploring Mochi on different types of video datasets is a clear next step, like video world models used for simulation or robotics. And then they're scaling it up even further.
Further than minutes?
Potentially, yeah. They mention an idea in the appendix called outer loop context routing. It's like adding another layer of hierarchy. This outer loop would first select really large-scale chunks of context, maybe entire scenes or chapters, before the innermost layers even look at them.
A coarse filter first?
Exactly. This could potentially allow scaling to millions of tokens, think extremely long videos, by drastically reducing the pool of tokens the main Mochi attention needs to consider at any given time. It's a path towards managing context for potentially arbitrarily long sequences.
Wow. Okay, so wrapping this up, what's the big takeaway here? It feels like Mochi is more than just another small step.
I think it really is a foundational shift. It tackles the core bottleneck of quadratic attention, not just as an efficiency problem, but as a memory problem. It shows that intelligent, learned sparsity, this idea of internal information retrieval, is a viable path to achieving true long-term coherence in generated video.
So the question this raises really is, if you can generate coherent, minute-scale video almost as cheaply as short clips, what does that unlock?
Right. What are the implications for content creation, for storytelling? Maybe even for scientific simulation. This paper provides a blueprint for building video models that can actually remember, that can maintain consistency over durations that were previously out of reach. It's about enabling scalable, controllable, and hopefully responsible long-form video generation.
It really changes the game. Imagine AI that doesn't just generate impressive short clips, but can actually keep track of characters, objects, plot points across a whole multi-minute narrative. So the final thought for you, our listeners, how might this capability reshape AI storytelling, and what kind of creative possibilities does this unlock for your work?